welcome to PCB Chat. This is Mike Buetow, Editor-in-Chief of Circuits Assembly and Printed Circuit Design and Fab. Dr. Puneet Gupta is Professor and Vice Chair of Computer Engineering in the Electrical Engineering Department at UCLA. He and his colleagues have been working on a new packageless semiconductor system referred to in some quarters as chiplets or dielets. Central to Dr. Gupta's research is the notion that the printed circuit board could be replaced with silicon. As he details in a recent paper published in IEEE Spectrum, they are calling this concept silicon-interconnect fabric. Welcome to PCB Chat, Professor.
Thank you.
Professor, your paper is titled Goodbye Motherboard, Hello Silicon Interconnect Fabric. Could you give our listeners a brief explanation of your chip-to-chip concept and what you hope to achieve?
So basically what me and my collaborators, Professor Subramanian Iyer in my department, we've been looking at for past couple of years is to develop both design techniques as well as technology to support them to allow us to get rid of packages and printed circuit boards. Now, the first thing that I have to kind of give a rationale for is why even bother? And the couple of reasons. First is that we all know that the so-called Moore's law has allowed for scaling of the chip dimensions and stuff you can pack into a chip by orders of magnitude over the last few decades, several orders of magnitude. In the same time frame, the packaging and the board dimensions haven't really scaled that much. So as a result, if you look at a modern motherboard and if you kind of rip apart everything, let's say take apart a package of a server class motherboard and look at what is the size of the package versus what is the size of the chip contained in the package cavity, you could easily find a factor of 10 difference. And that's basically because one of the biggest reasons why the package still exists is to do a fan out. Because your motherboard I/O dimensions or the BGA or LGA or whatever else are way larger than what chip I/O dimensions can comfortably be. And therefore, something needs to fan out from ordered tens to hundreds of nanometers or tens of microns to hundreds of microns. And that's one of the biggest things that a package accomplishes. Yes, it does a bunch of other stuff as well, providing some mechanical support, some rigidity to the substrate, etc. But one thing because of which package has been getting rid of package has been an insurmountable task is because of that. Now, if I want to get rid of the package, unfortunately, we can't just get rid of the package. The underlying organic substrate, which is the PCB, also needs to be revised so that dimensions on it are comparable to what's there on the chip rather than these 10 to 100x higher. And that's why we believe that we need to get rid of package and the PCB together. You can't do one alone. By doing this, what it does is bring any two chips or chiplets on this interconnection substrate much closer to each other. Instead of being order millimeters to sometimes centimeters away from each other, the neighboring chips, you could place them tens of microns away from each other. This firstly reduces signaling delay, signaling power, can potentially improve signaling bandwidth substantially between the neighboring chiplets. Second, what it does is, since the back-end integration substrate is no longer an organic substrate, but standard silicon wafer, patterning on it is essentially same as what foundries have been used to for decades. And that has scaled very, very nicely. So you can build wires which are hundreds of nanometers pitch rather than hundreds of micron pitch on them comfortably. And the IOs on them, instead of being large solder balls, these are essentially copper pillars, few single-digit microns in diameter. And that's why the number of IOs that you can support per chip increases by easily a factor of 10, if not more, by doing this. So that's the high-level advantages. There's other secondary advantages which are especially valuable for high-power chips, which is that unlike a PCB, which is again organic and pretty much a thermal insulator, silicon is actually a pretty decent thermal conductor. So as a result, by doing this packageless assembly on this, what we're calling a silicon interconnect fabric, you can extract heat from both sides rather than just one side. What I mean is, if you look at a normal motherboard right now, typically you will see package, and on package of the top of the package, typically, or at least for the high power things, a massive heatsink. And you will never see a heatsink on the bottom side of the motherboard. And the simple reason for that is you have essentially a piece of plastic sitting in between, which is an insulator. So now, if you get rid of that and we have silicon, which is a reasonably good conductor, then you can extract heat from both top and the bottom. And this can alleviate heat extraction issues, which is one of the biggest issues which limits how fast things run on modern machines, by getting rid of the package and the printed circuit board. So that was a kind of a sort of a long-winded answer to your question on why do this.
Now, as I understand it, the concept of this itself dates to Gene Amdahl, who is a legendary IBM computer designer. But Amdahl couldn't get it to work. Why not?
So Gene Amdahl, one of the most famous computer architects ever, what he tried, what his company tried, Trilogy Systems tried to do, was to build a single processor as large as a whole wafer. And this was in early 80s. And so you can think that even at that time, there was a strong incentive to do something like this. And the incentive has only grown by the nature of applications all of us want to run on clouds, data centers, supercomputers, etc. The why it didn't work out at that time was what Trilogy was trying to do was build one single monolithic computer on one single wafer. And as a result, they had huge yield problems, because certain things fail, and if certain things fail, you have to throw away the wafer, and if your chip is as big as a wafer, something or the other is bound to fail. So they tried hard, they tried a bunch of redundancy tricks, etc., but eventually gave up on this. So that's why primarily it didn't work out. In our approach, the end goal is somewhat similar, but the way to get there is completely different. We do want to build large systems, potentially wafer-scale systems, but we want to build them not by a single monolithic massive chip, but by assembling large number of small chiplets on the so-called silicon-interconnect fabric. So we have to ensure high yield on three things. On the small chiplets, and these chiplets could be as small as a millimeter by millimeter. So ensuring high yield on them is relatively straightforward. It's nothing new. Second, we have to ensure high yield on the bonding process when we kind of copy and paste these chiplets onto the fabric. My colleague Subbu Iyer's technology packaging work in the last few years has demonstrated that that's doable by the process that they have developed. So that's the second step. And the third is we have to ensure high yield on the integration substrate, which is essentially a silicon wafer. And that also is relatively easy for us for two reasons. One, our silicon wafer is completely passive. It contains absolutely no transistors. It's just wiring. And ensuring high yield on wiring is somewhat easier. And second, not only does it have no transistors, it does not have any ultra fine pitch wiring of today's technology. What it has effectively is similar to what would be top level metal layers in a 90 or 65 nanometer process. And ensuring high yield on them in commercial foundries at this point is relatively easy. So these three components of yield, we can manage it, and that's why we believe that we will not face the same yield problems that Gene Amdahl's work faced a couple of decades ago.
Would you anticipate that the bonding process would take place at the wafer foundry or downstream at a more traditional OSAT or even a what we would call an electronics manufacturing services provider?
That's a tougher question for me to answer per se. The bonding part itself, the silicon wafer fabrication could be done at a regular silicon foundry because it's no different from what they're used to. The chiplets could be manufactured, obviously, at the silicon foundry as well. And the final bonding itself could be either done at the CMOS silicon foundry or could be done by a third-party entity. That economics, I honestly don't know where it will end up with.
Fair enough. Now, in your testing, I believe you encountered some certain power limitations. What can you tell us about those, and how are you proposing to overcome them?
So the power limitations are mainly of a concern in when we start building these so-called wafer scale systems. The silicon interconnect fabric or this packageless integration can be done without being wafer scale at all, right? You could think of them as an approach to reduce the size of your quote-unquote motherboard equivalent. So we tried that out for fairly popular embedded class PCBs, and Embed, which is a very popular IoT platform, and BeagleBone Black, which was a very popular, I would say, low-end mobile phone class platform. What we found is, without any power or thermal limitations, you could essentially shrink the size of the board by a factor of 2 or 2.5, reduce the weight of the whole board, including the passives, the chips, etc., all on it, by again a factor of 2 to 5. And this can be achieved without any power or thermal issues. Now, where the power and thermal issues become very challenging is when you really want to build massive systems using this technology. Because we are able to pack much denser compute on the substrate. That's the advantage of it. But along with it comes the downside that the power density also proportionately increases. In a PCB, just by the very nature, things are very far spread apart, and therefore power density is, on an average, is somewhat lower. In our case, the power density can be very high because the compute density is very high. So we had done a canonical study with some collaborators at the University of Illinois as well, and what we found is that in theory we could cut and paste close to 70 GPUs on a single 300 millimeter wafer in terms of compute density. But once you account for the fact that you have to cool these 70 GPUs, each of them burning close to 300 watts, it becomes very, very tough task. You have to deliver this massive amount of power to the substrate. That becomes a very tough task. So at that time, what we did was we could basically, by playing a bunch of tricks, all we could pack in was about 30 to 40 GPUs, and remaining area was sort of underutilized. There are two ways that we are dealing with this. One is a more design methodology issue, where what we are doing is for power delivery, once you're trying to bring in kilowatts of power into this wafer scale substrate, especially if you're bringing it from the edges of the wafer, what we do is bring the power in at higher voltages and step it down near point of use. That has an obvious downside that you will actually use up a fair bout of silicon real estate on DC to DC converters and regulators. But still it allows us to bring in power without a massive amount of losses. The more speculative, slightly future goal of this is something that Professor Iyer and one of my other colleagues in the mechanical engineering department, they've been trying to develop, is what we have been calling as power therm, which is essentially bringing power from the backside by digging holes into the silicon wafer and propping in massive through-wafer vias, copper-based through-wafer vias. And that would allow us to bring in power without down conversion and much higher power delivery capacity. So that's the longer-term goal to eventually get there.
Have you been running into crosstalk issues in your testing?
Not that much. Remember, yes, we are fine pitch, but still we are talking about wiring which is at 2 to 5 micron pitch, which is what is used in normal chips already right now. Now, for signaling, we typically do use ground metal ground type of signaling, so the crosstalk issues, if any, are mitigated.
Now, in your paper, you tend to prefer the term dielet instead of chiplet. And what's the difference between a dielet and a system on a chip?
A system on a chip is completely different. So for us, this is a system on IF or system on wafer. Mm-hmm. The distinction between dielet and chiplet, that my colleague, Professor Iyer, strongly prefers the use of dielets versus chiplets, and the distinction is somewhat subtle on what that means, but the rest of the industry, unfortunately or fortunately, uses them more or less interchangeably. While system on a chip is somewhat different. System on a chip is what we build today, which is just a single chip which has a bunch of different blocks, IP blocks on it, doing different functions. For us, that would be replaced by system on interconnect fabric, where the IP blocks are not soft IP blocks, but prefabricated chiplets or dielets. And they are assembled together on this interconnect fabric.
Professor, where do industry standards come into play here? Right now, packaged ICs provide a clear path for designers of electronic systems.
Mm-hmm.
They have common footprints, they have dimensioning systems and routing paths that are generally well established using common ECAD tools. Assembly printers and placement machines have known recipes for placing and soldering components. If all that could go away, would you envision some consensus is needed, or would the industry be made up of solutions that are unique to every company?
There is already efforts that have started in inching the industry towards the direction of somewhat standardization for chiplets. So there is a fairly large DARPA program which has been running for a few years now. The goal is not getting rid of motherboards there, but the goal is still enabling chiplet-based design on what's called as interposers. And as part of that, there is already some standardization, at least across some fraction of the industry, on interconnect signaling protocols. So that direction is happening. Absolutely, you're right that we are still very far away from the level of standardization that exists in the package, socket, PCB community. But things are slowly inching towards that direction. And they will need to get there simply because the only way this ecosystem can flourish is if there is a wide variety of so-called chiplets available for system designers to integrate.
Finally, for listeners who want to be able to keep track of your research and advances in this area, where should they go?
In terms of work in both my group as well as Professor Iyer's group, who has been leading the technology end of things, the best place is Professor Iyer leads a center, which a big part of it is looking at this chiplet assembly-based integration, and that center is chips.ucla.edu. That would give a fair bit of information about this. Then in my group, we have been looking at more system architecture and design methodologies for this, and that is nanocad.ee.ucla.edu. And please be on the lookout. In a few months' time frame, we might hopefully be able to showcase a wafer scale processor assembled at UCLA.
Thank you, Dr. Gupta. My guest today has been Dr. Puneet Gupta, Professor and Vice Chair of Computer Engineering in the Electrical Engineering Department at UCLA. I truly appreciate you taking the time to explain the silicon-interconnect fabric.
Okay, thank you.
This has been Mike Buetow for PCB Chat. Have a nice day.